Hello, chemistry, and today we're doing 12.1, which is the volume to mass relationships of gases. I think this is our last chapter on gases. Yeah, our next chapter will be on liquids and solids, so gotta make it through one more. And this one's when we start to see some really useful um, equations. We've already used some really useful ones: Boyle's law, Charles' law, Gay-Lussac's law, and then Dalton's partial pressure. All very important equations. So in the early 1800s, Dalton and Gay-Lussac were both experimenting with gases. Gay-Lussac, he was, that is his full last name, was an early balloonist. They were just now starting this art of hot air balloons, and he was very involved in the process. He discovered that gases combine in small whole numbered ratios. You guys know that chemical equations happen in whole numbered ratios, but this was brand new for these guys. What this showed us was gases were not isolated atoms, but actually molecules. So, measuring and comparing volumes of reacting gases, Gay-Lussac noticed that when 2 liters of hydrogen and 1 liter of oxygen reacted, 2 liters of water vapor are formed. He found that this equation is always 2 parts hydrogen to 1 part oxygen. Whether it's 200 grams hydrogen, 100 grams oxygen goes to 200 grams of water vapor. He always found that it was this 2-1-2 ratio. What he didn't have right is he thought that it could happen and all these little molecules were discrete. They were one individual atom combined. So, Gay-Lussac's is at a constant temperature. The Gay-Lussac's law of combining volume of gases. Very wordy, very a little bit egotistic, but that's okay. It works. At a constant temperature and pressure, the volumes of gaseous reactants and products can be expressed as a ratio of whole numbers. So the 2-1-2, 1-1-1 for 1-1-2, excuse me, for like sodium, like HCl, hydrochloric acid. We most commonly use moles in our ratios instead of liters or grams or any other thing to use. Avogadro, he found a way to make Gay-Lussac's law work all the time, because at the time it was only working half the time. And instead of individual atoms, Avogadro said, hey, gases have to be diatomic. They have to be these 2 atoms bound together. Avogadro's principle is that equal volumes of gases at the same temperature and pressure contain equal number of molecules. So, oxygen contains the same amount of molecules. 1 mole of oxygen contains the same amount of 1 mole of hydrogen, even though hydrogen weighs 1 and 2, and oxygen weighs 30 something. So for Avogadro's law, over on the right there, K is a constant, and then N is the number of moles in gas. 1 molar volume of gas, you guys know 1 mole contains 6.022 times 10 to the 23 number of molecules. 1 mole of oxygen contains 6.022 times 10 to the 23rd number of oxygen molecules and weighs almost 32 grams. Hydrogen, 1 mole contains the same number of molecules and weighs a lot less. But because each one is 1 mole and has the same amount of molecules, the same number of particles, they should take up the same volume at a standard temperature and pressure. So the standard molar volume of a gas, the volume occupied by 1 mole of gas at standard temperature and pressure, is found to be 22.4 liters, 22.14 actually. So the sample problem in your book, which will look a lot like number 5 on your section review. This is the chemical reaction expected to produce 0.068 moles of oxygen gas. This is what you're starting with. Let's do it in blue. What volume in liters, this is your question, will be occupied by this gas at STP? That's some accessory information. So you're given 0.068 0.068 moles of O2. What they want to know is your volume of O2 in liters at STP. Moles of oxygen is equal to volume of oxygen. So you're going moles of oxygen to volume of oxygen at standard temperature and pressure. The standard molar volume can be used. So you start in moles, and you'll times it by this conversion. So there's your conversion factor right there. 1 mole is equal to 22 liters of a gas. So when you're computing, you put in your number from your equation, 0.068 moles, times 22.4 divided by 1 mole equals 1.52 liters. And that's the answer you're looking for. Oh, I can laser point too. Sweet. Okay. Gas density. Density represents the masses of equal numbers, the masses of gases with equal numbers of their molecules at STP. So the mass of oxygen is a lot heavier than the mass of, the density of oxygen is a lot more dense than hydrogen. Density is measured in grams over liters. So to find density, you take your molar mass and divide it by your molar volume. And that will give you your density. And that's what you'll be using for question number 6. You guys have any questions on your section review? You guys have 1 through 6 today. Please email me. Hope you guys are having a marvelous Thursday. One more day until spring break. And I'm just as excited for it as you guys are. All right, have a good one.